Welcome to this video. In this video, we're gonna talk about the uncertainty principle. Bohr is partially correct. He must have believed that the electron is revolving around the nucleus in a circular orbit and have attempted to predict the precise location of the electron at all times. Hence, this is still in a classical point of view. The planetary model has worked for the hydrogen atom, but not for all the elements. The derivation in the last video is made from de Broglie's approach that matter can exhibit wave nature. Hence, we have verified that there is a wave and particle duality. This work has to come a decade later. Hence, Bohr doesn't know about this. This makes his work all the more remarkable. From de Broglie, we know that the electron could have a wave motion, and this is related to the momentum of the electron. We have the formula P, or the momentum P, is equivalent to mv, is equivalent to n, which is the principal quantum number, times h, which is the Planck's constant, divided by the wavelength. We can write this in terms of the wave number k, because this is related to the wavelength of the electron. So we will see that momentum p is equivalent to mv is equivalent to n, which is the principal quantum number, times h, which is the Planck's constant, times k, which is the wave number, all over 2 pi. So the premise of the uncertainty principle, this is where the uncertainty came from. Are we all aware of the wave number at all times? Basically, no. If we are not aware, we are also not certain about the momentum of the particle at a given time. That's true. And if we are not aware, we are also less certain about the energy of the particle at any given time. So we can write an expression in terms of the infinitesimal change in the wave number gives an uncertainty of the momentum of the particle. So we have the formula, or we are going to rewrite the formula for the momentum in terms of the wave number. We have the momentum P, or the change in momentum P, is equivalent to mv is equivalent to n, which is the principal quantum number, h, which is the Planck's constant, and delta k, that signify the change in the waves, or the number of waves, all over 2 pi. So from the equation, delta p equals mv is equivalent to nh delta k all over 2 pi. We have an expression for delta k, and that is equivalent to 2 pi r all over the lambda, or all over the wavelength. Now we are trying to look for the source where the changes in delta k, in the change in the wave number is coming from. And since 2 pi right here is just a constant, there's no other source but the change in the wavelength. Alright, so this change in the wavelength is actually the change along the x-axis. Alright, so therefore, this is equal to the length traveled in the x-axis. So delta k depends on delta x. So we can write changes in delta k as seemingly equal to 1 all over delta x, because 2 pi r there is a constant. So we can actually get the product of delta k and delta x, so that we mean that they commutate, alright? Okay, so the degree that the quantity commutate as defined by probability is given by delta k times delta x is less than or equal to 1/2. Alright, so that's the a formula coming from the probability and statistics. So you can check if you want to And then we can write the new equation for this using the expression delta k, or the change in the wave number, times the change in the x position, all right, is equivalent to or less than or equal to 1/2. All right, so next is to show that delta k is equivalent to or less than or equal to 1 all over 2 delta x. Now we can plug this equation into the expression for the momentum that we have earlier, as delta p is equivalent to nh times delta k all over 2 pi times 1 is equivalent to nh all over 2 pi times 1 all over 2 pi delta x, because we know that 1 all over 2 delta x is just equivalent to delta k. And then we can simplify this as n times h all over 4 times delta x. And then what we need to do is to cross multiply to show that delta p, or the change in momentum, and change in the x-axis of the particle is equivalent to nh all over 4 pi, or equivalent to n times the h bar all over 2. So this formula can actually calculate the amount of uncertainty in the position and the momentum of the particle. So this is equivalent to a constant. If we let n is 1 for the hydrogen atom, we have the h bar all over 2. So that's gonna be h bar, all right, all over 2. All right. We will now write the energy-related uncertainty principle. So we remind of these questions and these premises, and we can use the expression E equals hf, which is this is given by Max Planck. All right, so E is the energy, and h is equivalent to the Planck's constant, and f is the frequency of the source. Actually, Einstein also used this in his formula for the photoelectric effect. And we have a formula for the frequency, which is f is equivalent to 1 all over t. And then the accuracy of measuring the energy released during an atomic process depends on the amount of time available for us to observe it. So basically, this is limited by this thing, or this variable over here, time. So if there is a change in time, and we can show that in the next expression, there will be a change in the amount of energy that we are gonna measure. So the uncertainty in the measurement of the energy has something to do, and is limited by the delta t. All right, so you just have to cross multiply delta E times delta t, and you'll see that that's equivalent to less than or equal to h. But there are more precise formulation of this, and this is related to the wave groups, and we can show that the uncertainty principle for energy and time is less than or equal to h all over 4 pi. So this is due to the limit, okay, of measuring capability, and since there are errors, so we have to correct ourselves within a certain limit of uncertainty. All right.